we present a new method for generating realistic and view-consistent images with fine geometry from 2D image collections. Our method can handle challenging view angles and synthesize articulated objects with high spatial degree of freedom. A trend in the studies of 3D volumetric representations is to use codebooks with explicit spatial structure in conjunction with an implicit function for improved representational capacity. Voxel codebooks store scenes with grid-distributed feature points which are interpolated trilinearly upon query. Multi-resolution hash table uses multiple voxel grids with different resolutions to store different levels of features. These representations can encode individual scenes well but are hard to create. The triplane representation takes 3D spatial points and projects them onto three featured planes that are placed orthogonal to each other. Then, it joins the 2D feature vectors where the projections land to use as a 3D feature. The feature planes can be easily generated by modifying StyleGAN2 generators. Though computationally efficient, we argue that this representation has limited 3D awareness and suboptimal scalability. We propose OrthoPlanes, which encodes fine-grained 3D information in feature maps that can be efficiently generated by modifying the 2D StyleGAN. Inspired by successful scene-specific representations, we find that sectional projection can better represent the 3D world than orthogonal or parallel projection. This is because sectional projection has better spatial granularity and provides more explicit 3D information, such as the projection direction and the distance. To generate 3D-aware images of random objects, we first generate k times 3 feature planes with a modified StyleGAN2 generator. Next, we form an OrthoPlanes codebook by placing the feature planes orthogonal to each other, creating a compact and expressive representation of 3D scenes. Then, we query the codebook during neural rendering to synthesize images from desired view angles. After that, we upscale the rendered images with a super-resolution module to enhance their resolution and quality. Finally, we use a dual discrimination scheme to ensure consistency between the rendered and upscaled images and to train the network in an adversarial manner. Here we examine the generator architecture that is modified from StyleGAN2 to generate OrthoPlanes. First, it is a style-based generator, which means that it is a 2D convolutional network that is modulated by a mapping network. In our design, location embeddings are also used as a modulation for better spatial awareness. The 2D convolutional network is formed by a series of synthesis blocks. Each synthesis block has two branches, one for generating intermediate features for the next block, and the other for generating the orthoplanes. This is where the location embeddings are injected. Notice that orthoplanes features are generated after each block. These features are concatenated to form the query-ready orthoplanes. We evaluate our method on 3 datasets, FFHQ and AFHQ, which are widely used for image generation, and SHHQ, which contains challenging full-body human images. Our method surpasses the state-of-the-art 3D-aware image generation methods in terms of image quality on FFHQ and AFHQ. In particular, our method improves the FID score by 15% over EG3D. The superiority of our method is more evident on the SHHQ dataset, where many methods fail to train due to excessive computational costs. Our method achieves a remarkable FID score of 4.18, which is 28% lower than EG3D. In qualitative comparisons, we closely inspect results from our method and the former state-of-the-art EG3D. Both methods can produce realistic frontal views for the FFHQ dataset. However, when the angle of rotation is large, e.g. 3D results have some artifacts, while our method preserves the image quality and especially the fine details. One might wonder how OrthoPlanes compares to e.g. 3D with larger resolution or number of feature channels. We test different upscaling methods and find that our method benefits the most from adding more feature planes with relatively small computation cost compared to upscaling e.g. 3D. In the ablation study, we examine the effects of the number of feature orthoplanes used and the type of location embeddings. When increasing the number of feature planes, the results resonates with the intuition that network with more planes can capture more information. Also, the model with frequency-based location encoding shows improvement on image quality and geometry. Our method supports smooth interpolation of appearance. In this experiment, we generate images by mixing coarse and fine-level styles from different latent codes. With a coordinate transformation based on inverse linear blend skinning, we can achieve pose conditional generation with SMPL meshes.